So for this video, I want to show you kind of systematically, first how to find nth roots of unity, then how to find nth roots of more general numbers. For today, I'm going to focus on nth roots of some number a, where a is a real positive number. And then we'll talk about how to factor polynomials of the form x to the n minus a. First, allowing your factors to have complex coefficients, and then allowing them to have real coefficients. Okay, so nth roots of unity. What we're really looking for are solutions to the equation x to the n minus 1 equals 0, or x to the n is equal to 1. And what we want to do is use complex numbers and write this in polar coordinates. So suppose x is a solution, then I'm going to write it in polar coordinates as r e to the I theta, which remember just means that this number has distance r from the origin and an angle theta from the real axis. So if here's my angle theta, and here's my distance r, then this is the point x. Okay, so if that's x, then x to the n, because of how we multiply complex numbers in polar coordinates, has the form, well, the radius gets taken to the power of n, and the angle theta gets multiplied by n. So if x to the n is equal to 1, then we could write 1 in polar coordinates. This is 1 e to the I 0. In other words, its radius or its modulus is 1. Its angle is 0. So this tells me then that r to the n has to equal 1, and n times theta has to equal 0, or an angle that's equivalent to 0, which is 2 pi, 4 pi, etc. Any multiple of 2 pi. So let's do an example. Let's say n equals 5. So I'm trying to solve the equation x to the 5 is equal to 1, and x is r e to the I theta. We already know that r to the 5th is equal to 1. So r is a non-negative number whose 5th power is 1. That means r has to equal 1 as well. And then 5 times theta is equal to 0, 2 pi, 4 pi, etc. Which means if I divide by 5, theta has to be 0, or 2 pi over 5, 4 pi over 5, and I'll keep going, 6 pi over 5, 8 pi over 5, 10 pi over 5. But notice that 10 pi over 5, that's the same as 2 pi, which is equivalent to 0. And so this angle here was already counted here. And so I'm back to where I started. And if I keep going, I'm just going to get repeats. And so the roots are exactly 1 times e to the I times 0, 1 e to the I 2 pi over 5, 1 e to the I 4 pi over 5, and similarly with 6 pi over 5 and 8 pi over 5. And so we get 5 roots. And if I draw a picture of this, all of these have distance 1 from the origin, which means they lie on the unit circle. And the first one lies on the positive real axis. And then the rest are evenly spaced around the unit circle. Oops. Try to draw them sort of accurate. Something like this is the fifth roots of unity. So this one's at 2 pi over 5, 4 pi over 5, etc. Okay, so that's how you find fifth roots of unity. And once you know how to find roots of unity, you can really find roots of any positive real number quite easily. So if you want, for instance, fifth roots of some number a, let's say a is greater than 0, and it's a real number, then, well, it has a real root. Positive real fifth root. Which we usually denote like this. And all of the others, all the other roots are going to have this as their r, as their distance from the origin, and the angles are going to be the same as before. And so what we get is that the roots are fifth root of a, which is the same as fifth root of a times e to the I 0. And then I just change the angles like before. So then I add a 2 pi over 5, 4 pi over 5, etc. So all that changes is the modulus, and the angles stay the same. And so then the nth roots of some number a greater than 0 are all of the form r e to the I theta, with r equal to the positive real nth root of a and theta 1 of 0, 2 pi over n, 4 pi over n, etc., all the way up to 2 pi times n minus 1 over n. And then if I went one more to 2 pi times n over n, that would be 2 pi, and that would be something I've already gotten written down. Okay. So that's how you find roots of positive numbers. What I want to talk about next is how to factor polynomials. So an important fact is that p of x is a polynomial with real coefficients. So it's equal to some a sub d, x to the d, plus ad minus 1, x to the d minus 1, etc. Then, oops, if c is a complex number, which is a root of p of x, meaning that if I plug it in for x, I get 0, then the claim is that the conjugate of c is also a root of p of x. And the proof is really nice. So I just write down this equation. So suppose p of c is equal to 0, then I can conjugate both sides, and I get that the conjugate of P of C is equal to the conjugate of 0, but the conjugate of 0 is just 0. But now I want to expand what this actually is. So this is AD times, so P of C is equal to AD times C to the D plus AD minus 1, C to the D minus 1, etc. U1C plus A naught. So this is P of C. And now if I conjugate it, I know that that has to also equal 0 by this equation. But what happens to the left-hand side here? So the conjugation operation commutes with sums and products. And so this becomes AD conjugate, C conjugate to the D, plus AD minus 1 conjugate, C conjugate to the D minus 1, etc., plus A1 conjugate, C conjugate, plus A naught conjugate equals 0. And here's where we use the fact that we're assuming that our coefficients are all real. So since these are real numbers, their conjugate is just equal to the same number. Conjugating a real number doesn't change it. And so what we get is that this, the conjugate of AD is just AD. So this is just AD times C conjugate to the D, etc. So this is equal to 0, but you notice that this expression here is exactly what I get if I plug in C conjugate to my original polynomial. And so I conclude that P of C conjugate equals 0. Okay, so that's the proof. Let me state the result again. So if I have a polynomial whose coefficients are all real numbers, then whenever I have a complex root, its conjugate must also be a root. Okay. So as an example, if I'm looking at the nth roots of A, let's just look at the roots of unity here. X to the 5th minus 1, this is a polynomial whose coefficients are real. Coefficients are 1 and minus 1. And so what that result tells us is that whenever I have a complex root, its conjugate must also be a root. And we see that here. Here's a complex root, and its conjugate is exactly this. So the conjugate of e to the I 2 pi over 5 is e to the I 8 pi over 5. Because you can see these two numbers have the same real part, but opposite imaginary parts. And similarly, this root of this polynomial, its conjugate is also a root. So we see it in this example. Now here's some other nice facts. Suppose I have a complex number C. So it's some x plus iy. Then it's pretty easy to see that, first off, C plus C conjugate is real. Why? Well, this is equal, the imaginary parts cancel, right? So this is just 2x. And furthermore, C times C conjugate is real. You can compute that this is equal to the square of the modulus, or the square of the distance from the origin of C, which is just x squared plus y squared. So in fact, it's real and non-negative, but we won't use that. And these two facts together imply that if I take the polynomial x minus c times x minus c conjugate, this is going to have real coefficients. Because what is this? This is x squared minus c plus c conjugate times x plus c times c conjugate. And so this part is real, and this part is real. So this polynomial has real coefficients. Coefficients. We're going to use this fact to factor certain polynomials. Into their prime factors. With coefficients in R. So first, we factor with coefficients in C. So step one, we factor this polynomial, allowing coefficients to be complex numbers, but we know how to do that because if C is a root of the polynomial x to the n minus a, in other words, if c to the n is equal to a, then x minus c is a factor of this polynomial. It divides the polynomial x to the n minus a. Here, again, we're assuming that a, let's assume that a is a real number greater than 0. So every nth root of a gives me a factor of this polynomial. There's exactly n nth roots, which means I have exactly n factors. And at the beginning of this video, we figured out exactly what the nth roots were. So the nth roots are the real nth root, and then nth root of a times e to the 2 pi I over n, etc. 4 pi I over n. And then n minus 1 over n times 2 pi I. And so this gives me the factors. So this is how you factor over the complex numbers. And then to find the prime factors where you're only allowed real coefficients, you have to match up x minus c with the other factor, x minus c conjugate. Because remember, if c is a root of this polynomial, its conjugate is as well. And the product of those two is going to be a polynomial with real coefficients. So let's do the example x to the 5th minus 1. So first, we write down the complex roots, and we get those factors. Well, we wrote the roots down above. So this is x minus 1, x minus e to the 2 pi I over 5, x minus e to the 4 pi I over 5, etc. And we want to group these roots according to their conjugates. So this is the factorization over the complex numbers. But since 2 pi over 5 plus 8 pi over 5 is 10 pi over 5, which is a multiple of 2 pi, that means these two are conjugate to each other. And similarly, these two are conjugate to each other because 4 plus 6 over 5 is also 2. So I'm going to rewrite these. Grouping them by their conjugates. And I know that whatever this product is, since it's x minus some c and x minus the conjugate of c, it's going to be a polynomial with real coefficients. And similarly for this one. Yeah, but to actually write it out, you would have to put this into rectangular coordinates to get a nice expression for the product. So maybe I'll leave that as an exercise since it requires a calculator.